Hi, welcome to this video looking at inductors and the energy stored in an inductor in a DC circuit, part of the Advanced Higher Physics unit on electromagnetism. So these are the things that we're going to look at today. We're really just going to look at the energy stored in an inductor and the relationship and go through some examples to help you solve problems using that. Inductive reactance will be found in one of the later videos. So inductors can store energy in the magnetic field that exists around them, and this energy can be released very quickly when the field collapses and a large EMF can be produced as a result of that. This EMF can be much greater than the EMF of the supply that was used to store the energy in the magnetic field in the first place. So in a similar way to energy stored in a capacitor, where the energy is half times the capacitance times the voltage or potential difference squared, the energy stored in a conductor is half times the inductance in henries times the current squared. This can be released very quickly when a large coil is switched off, and we can get a large spark which can damage equipment, result in loss of data or an electric shock. So circuits with inductors often have diodes in them to protect them from this back EMF, which would damage the equipment from there. Okay, so as mentioned, the energy stored in the inductor is equal to half times the inductance times the current squared. And this relationship is on your relationship sheet. We can derive the relationship by considering the power. So we know that the power is the current times the voltage, and for an inductor the back EMF is equal to minus L di by dt, so that the power can be written as I times L di dt, and since power is the rate of energy per second, we can end up with the relationship that dE is equal to L I di. So then if we integrate both sides with respect to E on respect to I, then when we integrate I, with respect to I, we get I squared divided by 2, with the L being the constant. Okay, you don't have to be able to show this, but this is just to show you where it does come from. So we can work out the energy stored in a magnetic field on a particular inductor by substituting in the particular values that we've got. So if we've got a 4 Henry inductor and 300 milliamps of current, then the energy stored will be half times 4 times 0.3 squared, which will be 0.18 joules of energy. Okay, here we've got an example of using a 6-volt supply, which is connected to a neon bulb, this one here, and you can see that the bulb doesn't light up because it actually needs about 60 volts for it to light up. But when we connect those 6 volts supply to our inductor here, and we've got in the circuit there, so you can see the inductors in parallel with the neon bulb supply that has 6 volts. And then when we press the switch, we see that the bulb doesn't light up, but when we release the switch, you will see that the bulb will light up temporarily. So pressing the switch, nothing happens, and releasing the switch, if you look really closely, there's a tiny flash of light. So it's lighting up this 60 volt or even 90 volt bulb that it says on here. You can see the full video at the bottom here. So how do we explain that one? Okay, so if we've not got sufficient voltage across the bulb, then the bulb is a bit like an open circuit there. When we close the switch, the current passes through the inductor to reach its steady value of the supply EMF divided by the resistance, where R is the resistance of the inductor, and the energy stored within that magnetic field is half times Li squared. When we open the switch, there's a change in the current, so we get a back EMF that flows across the neon bulb, causing it to light up. And this happens over a very small time, so we're able to get much higher voltages than we got from our cell to begin with. So we could summarize this two ways. We could talk about the magnetic field collapsing rapidly when the switch is open, so we get a large rate of change in current. This induces a very large back EMF for a very small time, lighting up the bulb. Or we can talk about it from an energy point of view, that when the switch is closed, energy is stored in the inductor. When we open the switch, the energy stored in the inductor is released to light the bulb. The energy stored can be really large. We've got two large solenoids with iron cores here and a resistor and a power supply and a switch. The person's going to pull the switch. You can see the wire moves because of the field, and they open the switch and you see that large spark that's taking place as they do that. So let's have a look at a past paper example. So we have a circuit here with 3-volt battery, a switch, 30 ohm resistor connected in series with our inductor, which has an iron core. You can see from the line, remember, and the inductor with the iron core is connected in parallel with the neon lamp. And we are asked to sketch a graph to show how the current in the inductor varies with time from the instant the switch is closed, with appropriate numerical values on the current axis. Okay, so the graph will look like this one. The inductor is opposing the rate of change of current, so it will take a little bit of time to reach its maximum value, and the maximum value can be determined from Ohm's law, 3 volts divided by the 30 ohms of resistance, because we're assuming that the inductor has negligible resistance, as it tells us in the question. Remember, when we make a sketch here, we need to include the origin. We should have the right shape, and we should have labels of current and a unit, amperes, and time, and ideally a unit for time, but it's not always required. And we need to have that 0.1 amperes label on the axis. So the neon lamp requires a potential difference of 110 volts across it before it lights. Explain why the lamp does not light when the switch is closed. So when the switch is closed, there is no energy stored in the inductor, and therefore the maximum voltage can only be the same as the supply voltage, 3 volts. So the back EMF is too small to cause the neon lamp to light. After a few seconds, the switch is opened and the lamp flashes. Explain in terms of the magnetic field why the lamp flashes as the switch is opened. So the magnetic field collapses very quickly, and this means that the large back EMF of 110 volts is produced. And the back EMF can be much greater here because of the energy stored within the inductor, and therefore that can make it greater than the 3 volts that was supplied initially, because this happens over a very small fraction of time. The neon lamp has an average power of 1.2 milliwatts and a flash that lasts 0.25 seconds. Assuming all the energy stored by the inductor is transferred to the lamp, calculate the inductance of the inductor. So from the information about the power and the time, you can work out the energy that is required for that. And then that is the energy that must have been stored within the inductor. And based on the current from the previous question, the maximum current 0.1 from 3 volts divided by 30 ohms, we can work out that it's 0.06 henries. So during this video, we've looked at the relationship to calculate the energy stored on an inductor and how to solve some inductance problems using this relationship.